Hello there, welcome in this new video in the linear algebra video course. Today we'll have a look at the exam of September 2025. As usual, when you're preparing your exam, well, have a look at the questions, push the pause button and try to do these exercises by yourself. So let's go ahead with the first question, in which you have to consider a matrix and find the values of a and b for which this matrix is invertible. For those values of a and b, you have to compute the matrix inverse. It's time to push the pause button. Well, let us have a look at the first question. Well, first of all, when is this matrix invertible? When its determinant, of course, is different from 0. Here it's quite straightforward to compute the determinant. It's a squared plus b squared, so the condition on a and b is simply a squared plus b squared different from 0. In order to compute the matrix inverse, what we do is we take A, and right next to it we stack an identity matrix, and then we start performing Gauss-Newton elimination. So here we assume that A here is a pivot. Of course we have to assume that A is different from 0, and we'll have to treat the case with A is equal to 0 separately, right? So here A is different from 0, so what we can do is this row elimination here with this multiplier b over a. This produces the following augmented matrix, right? And now we see that we have zeros below the pivots, right? So what we have to do is now create zeros above the pivots. So this one has to be eliminated, right? If you do the calculation, this one can be rewritten as so. So in order to create a 0, we have to do this row elimination over here, or this elementary row operation that will create a 0. And this is what we have obtained. We have almost an identity matrix here. What we have to do is multiply by 1 over a. This is not a problem because a is different from 0, and then multiply by a over a squared plus b squared. This is not a problem because a is different from 0, and this is what we obtain. We have an identity matrix, and we have shown in the course that what we produce over here is the inverse of a. We still have to treat the case a is equal to 0 separately. So what I've done here is written this augmented matrix with a is equal to 0. So what we have to do here is do, well, interchange of two rows to bring the third row at the first place, and this will become the pivot over here, right? This is, well, a diagonal matrix, right? So what we'll have to do to produce an identity matrix over here is simply multiply by 1 over b and by minus 1 over b. And of course, this will presuppose that b is different from 0. And if you do this, well, this is what you obtain. So this is a minus 1 when a is equal to 0 and b is different from 0. But if you look at it, this is exactly the same thing as over here, right? So if a is equal to 0, this one will disappear, this one will disappear. A is equal to 0, so you have 1 over b here, and here minus 1 over b, and this is exactly what you have over here. So we can take the result that we have over here, right? Rewrite it, and of course write our condition that the sum of a squared plus b squared needs to be different from 0. And this concludes the exercise. Well, let us now have a look at the second question, which is a really standard question for a linear algebra exam. So you have to find the values of a and b for which the system ax is equal to b has no solutions, an infinite number of solutions, and a unique solutions. For these values of a and b, where you have an infinite number of solutions, you have to express this solution in full detail. If you're preparing your exam, it's time to push the pause button. So let us have a look at this exercise. What you have to do is to take the A matrix and stack the B vector, in this case, next to it, and then perform Gauss elimination. So here we have a pivot -2. We can create zeros in the second, third, and the fifth line by doing these elementary row operations, and this is what you obtain, right? So next we obtain the following augmented matrix. So here we have A minus 1. A minus 1 is a pivot only if A is different from 1, right? So A equals 1 will be a special case that will intervene in the discussion. This is what you see already over here, right? So what we'll do is create zeros below this new pivot. This can be done by these two elementary row operations. This is what we obtain. And again, we can create zeros below over here using these two elementary row operations. By the way, we have a new pivot, A minus 3. Same thing. A equals 1 and A equals 3 will be special cases, right? If you do these elementary row operations, this is what you obtain. You can clearly see that if A is equal to 3, we have 0, 0, 0, and on the other side 2. So 0 can never be equal to 2. When A is equal to 3, there are no solutions, right? If A is equal to 1, you can rewrite this augmented matrix. Here it is. And then it depends on the value of B. If A is equal to 1, right? So this is this augmented matrix here. And you set B to -2. Well, these two equations, they tell the same thing, right? We have 3 variables and only 2 equations, so you have an infinite number of solutions, right? If A is equal to 1 but B is different from 2, well, you have 2 incompatible equations over here, so you have no solutions, right? And if A different from 1, different from 3, right? Well, the matrix has rank 3. There are 3 variables, so there is a unique solution, right? So this is the discussion, right? And what we have to do, don't forget to do this at the time of the exam, is have a look at this solution in detail when A is equal to 1 and B is equal to -2, right? So if A is equal to 1 and B is equal to -2, I have rewritten things over here. So what you have is a pivot over here, a pivot over here. We create zeros below and above using these elementary row operations. This is what you obtain. You multiply by -0.5 and 0.5 in the first and second line to have pivots that are 1. You interchange the columns over here, and here we have this standard form that we have seen in the course. This is the F matrix, it's a vector over here, and here dp with the same notations as in the course, right? And we have seen that we can find a particular solution. This is simply by writing things like this, right? We take this dp, put a 0 below. Don't forget that what we have written here is for this case over here, but we have interchanged 2 columns. So what we should do is here interchange 2 rows. And then we have the, well, the N matrix, right? And this is -f, and below you have to stack an identity matrix of dimension n minus r. N is the number of columns, 3, and r is the rank of the matrix, and you can clearly see that the rank is 2. So it's simply a scalar. Again, what you have to do, right, is since you have interchanged 2 columns over here, you have to interchange 2 rows, right? So, well, the solution can be written as xp, the particular solution, plus alpha times, well, the columns of n. So there is only one column, so alpha times this vector over here. And this concludes question 2. Let us now have a look at question 3, a question about least squares and the QR decomposition. So a step response from equilibrium, so this means yk is 0 for k negative, of a system that is described by a recurrent equation that is shown on the screen produces, well, the first four values of this step response, y0 to y3. And you want to use these values to estimate the parameters that come into play in this recurrent equation. And these values are a1, a2, and b0. You have to write this estimation problem as a least squares problem for general values y0 to y3. Once you have written this estimation problem, you should solve it using the QR decomposition for given values of y0, y1, y2, and y3, and then decide if using the QR decomposition is the most appropriate method in this case, and of course explain. Well, let us now have a look at the solution of the problem. First of all, we have to write this as a least squares problem in a matrix format. We take this recurrent equation and we evaluate in 0, 1, 2, and 3. If you do this, for instance, for k is equal to 0, you'll have y0 is a1 y minus 1 plus a2 y minus 2 plus b0 x0, right? These two here are 0 because of the initial conditions, right? And since it's a step response, this one is 1. So you end up with b0. We can do, for instance, the same thing for k is equal to 1, and you'll end up with this quantity over here, y in k is equal to 2 and y in k is equal to 3. So these ones you put in the b vector, right? The unknowns are a1, a2, and b0. You can stack them in the x vector, and the rest you put in the a matrix, right? So we have a least squares problem in matrix format. You can see that this is not really appropriate for a solution with the QR decomposition, because in the A matrix you find the elements of the step response. For each system there will be a new step response, right? So the A matrix will change with the estimation problem, right? You tend to reserve this decomposition using the QR decomposition for problems, least squares problems, where the matrix A is fixed. Let us now put in the values of y0, y1, y2, and y3 that are given over here. And, well, this is the least squares problem we have to solve using the QR decomposition, right? Well, let us now, with the actual QR decomposition of A, really we keep the first column of A, right? We have to normalize it, right? So this will be the first column of Q. Then what we do is we take the second column of A, and what we have to do is really subtract its projection on the first vector, right? And then we end up with this vector over here, which is by chance normalized, right? What we'll do to compute A3 bar is not work with this one over here, because this one contains thirds. This will make the computations complicated. We'll work with this one, which is in the same direction, but which is not normalized to 1 over here, right? In this computation, what matters is removing the projection of the third column on the second vector, right? And since we normalize over here, it doesn't matter if you work with this vector or with this one, right? The easy way to do it is to work with this one, because this is making the computations simpler. So A3 bar, we take the third column of the matrix A and we remove its projection on A1 bar and A2 double bar, right? If you do the computations, this is what you obtain. Well, to make the normalization to length 1, usually work with the same vector here but multiplied by 9 here, so that the computations would be easier, right? And then you can easily see that the length of this vector is square root of 90, so you have to divide by the square root of 90. So now we have q1, q2 and q3. You can stack them one next to the other and you have the Q matrix. To compute R, well, you have to do the computation Q transpose A. This comes from, of course, A is QR, right? And if you multiply on both sides by Q transpose, right, you obtain the R matrix, because Q is, of course, an orthogonal matrix. So this is Q transpose, this is A, and when you do the calculations, of course, you should obtain an upper triangular matrix. Do the computations to see if you indeed you have zeros over here. This is a check. Now we have the QR decomposition, and now we have to solve the actual least squares problem. You can transform this problem AX is equal to B to RX is Q transpose B, right? So we'll compute Q transpose B. Here we have Q transpose, here we have the B, this over here. If you do the calculations, this is what you obtain. And now you can write this problem here. Rx is Q transpose B, here it is, and now what you can do is back substitution. Here you can clearly see that this yields B0 is equal to 1, so 1 times A2, right, will be minus 4/3, and you take this one on the other side, right? So this will be plus 1/3 B0. If you do the calculations, you have A2 is equal to minus 1. You have B0, you have A2, and using the first equation, not that difficult, you easily find that A1 is equal to 1. So we have solved our estimation problem using the QR decomposition. And this concludes question 3. Let us now have a look at question 4, which is also a rather standard question in a linear algebra exam. So you're given a matrix A, which is parameterized by 2 parameters A and B, and you have to compute for which values A and B this matrix is positive definite. Then for values A equal B equal 4, you have to compute a factorization A is equal R transpose R, one that is related to the pivots and one that is related to the eigenvalues. If you're preparing your exam, it's time to push the pause button. Well, let us now have a look at the answer of question 4. So first of all, we have to look at the values of A and B, which make this matrix positive definite. Obviously the matrix has to be symmetric, so A is equal to B, right? So what we'll do is compute the upper determinants. So the first one is this one over here, so that's 5. The next one is this one over here. It's quite easy to compute, it's 39, so they are both positive. And so now we have to have a look at the determinant of A. If you compute it, right, we've computed it based on the first row, this is what you obtain, right? This determinant has to be positive. So what I've done is imposed that it's positive, and I've divided the equation by 2. So this is what you obtain. You can compute the roots of this second order over here, and there are 5 and minus 19 over 4. So it has to be in between the roots. For instance, 0 is in between the roots, and if you plug in 0, you see that it's positive. So A equals B, smaller than 5 and larger than minus 19 over 4. And you see that A is equal to B is equal to 4, well, meets this condition, right? So if you take the matrix A and replace A and B by 4, this is what you obtain. And we'll have now a look at the eigenvalues and eigenvectors of this matrix. So what we have to do is compute the determinants of A minus lambda I. If you do this, a minus lambda I, this is this determinant over here. You could compute the determinant of this one, but the computations will be quite difficult. So it's a good idea to kind of produce a zero over here. And it's kind of easy to obtain a zero, for instance, in the first column, if you replace the first column by the first column minus the third. And this is what you obtain, right? So we can now compute the determinant based on the first column. And what you see over here is that you have 1 minus lambda and lambda minus 1. So here it's already obvious that one eigenvalue is 1. Lambda is equal to 1. If you construct this determinant and you go over the calculations, this is what you obtained. Here you can clearly see that you have a second order polynomial and that the two roots are 7 and 10. Obviously you should check the trace of this matrix is, well, 18, and this should correspond to the sum of the eigenvalues, so this is correct. You also have access to, well, the determinant of A. If you plug in A is equal to 4 in here, you have the determinant of A. This is 70, and this corresponds to really the product of the three eigenvalues. So we are sure now that our values lambda 1, lambda 2, and lambda 3 are correct. You can also see that the three eigenvalues are positive, so this is an extra check to see that this matrix is positive definite for A equals B equals 4. By the way, I forgot to tell you that I can do these column operations because of course they preserve the determinants, right? So now we have the eigenvalues and we need the eigenvectors. Remember that an eigenvalue is a value lambda for which you can find a vector such that AV is lambda V. So when you go through A, you have a vector in the same direction, right? So we have lambda and we need the eigenvector. One way to write this is simply by saying that A minus lambda I V is equal to 0. So this is what we'll be doing for lambda equals to 1, lambda equals to 7, and lambda equals to 3, right? If you plug in lambda 1, this is the system of equations that you obtain, and obviously it's a good idea to do some row operations to produce some zeros over here to make it easier to find v1, right? And v1, then you have to give it a length 1, and this produces q1, which is the first column of q in the decomposition of A, q, lambda, q transpose. You can do something similar for the two other eigenvalues. Here I have used notations that are a bit non-standard. What this means is that I have taken 2 times the second row, right, and added the first row to produce a 0 over here, right? So this allows us to compute v2, v3, and of course you have to give it a unit length, right? And now we have the matrix Q, which is simply obtained by stacking Q1, Q2, Q3 as follows, right? As we know that A is Q lambda Q transpose, well, one of these two factorizations, the one related to the eigenvalues, if you set R transpose R, well, you can see here that R will simply be the square root of L. Remember that L is a diagonal matrix with the eigenvalues on the diagonal, so you can really write square root of a lambda. So this is square root of lambda. Since these eigenvalues are all positive, you can write this, and then you have to multiply by Q transpose. At the time of the exam, it's not necessary to do these calculations, right? But you should write this development. Well, let us now have a look at the factorization of A related to the pivots, right? Therefore, we need to compute the LU decomposition. So this is the matrix A. What we'll do is, well, produce zeros below the pivot, right? We have a pivot over here, and we can create two zeros over here using these two elementary row operations. And here it's very important to use these conventions with a minus sign, right? So this means row 2 minus a fifth of a row 1, right? Because we'll use these multipliers to construct the L matrix, right? So if you do these two elementary row operations, this is what you obtain. We have a new pivot over here that is indeed again positive. We need to create a 0 over here, and therefore we have a new multiplier. The computations are a bit heavy, but not that difficult, right? And you obtain U over here. Here are the pivots, and again they are positive, so it's again a check that this matrix is positive definite for A equals B equals 4, right? How do we construct L? We take an identity matrix, right? And in here we stack these multipliers. 1/5 is the multiplier that is used to produce a 0 over here, so this means that it has to go over there, right? And something similar for these two multipliers. So we have L, right? We can compute or construct a diagonal matrix with the pivots on the diagonal, and then from the course we know, and you can clearly see it also, A is L D L transpose. And if you want a factorization R transpose R, you can clearly see that R should be square root of D times L transpose. But this is written over here. You can write this, right? Because the pivots are positive, right? So this is really square root of D times L transpose. Again, you don't have to do the computations at the time of the exam. Well, you have just to write the development that is over here. So this concludes question 4, and this also concludes this exam of linear algebra of September 2025.